Let's get started with a nice lecture of topics in reinforcement learning. And in the preceding lectures, we have focused on deterministic problems, and we have introduced various methodology to address deterministic problems involving approximation in value space, rollout, and multi-step lookahead, and trying to take advantage of the problem structure in order to enhance the computation or limit the amount of computation that is needed in the minimization calculation. In this lecture, we're gonna shift gear and looking at stochastic problems, whereby there are stochastic quantities involved in the problem. Therefore, it's necessary to compute expected value, as I'm gonna go to shortly. And this means to accommodate this kind of situation with random quantities and so on, for a given state, it's not possible to run one simulation. You need to run multiple simulations, and this is a major challenge, and we're going to deal with that. First, we're going to deal with that within the context of one-step lookahead. Then we're going to talk about multi-step lookahead, focusing on rollout, but some of the ideas also apply for more generally in approximation in value space. And in multi-step lookahead, what is important is to take advantage of the or to minimize the computation simulation required, the sampling process required, while at the same time to evaluate various control options as adequately as possible. One of the major approaches is certainty equivalence, which we're going to cover, and the other approach is Monte Carlo Tree Search, whereby using certain statistical method or some criteria developed from statistical argument and try to allocate sampling effort to the ones that is most promising or most or least explored. And we're going to go to this methodology as well. And after that, we're going to talk about a different kind of problem, which is adaptive control problem, where we formulate the problem as a POMDP. And in this particular context, the expectation can be computed exactly. And this expectation is with respect to some belief distributions as we will go to. And we will talk about how to solve it approximately using rollout. And we're going to apply this methodology to a puzzle problem, which is Wordle. We have touched upon this problem earlier in first lecture, and we're going to provide more details. Okay, one step look ahead as a special case of approximation in value space. At this point, you are all familiar with this figure. At a given state xk, we want to minimize over all the feasible control. The sum of the current stage cost plus a function that represents the future cost. And as in the deterministic problem, there are a few challenges. One is how to solve this minimization problem when the control constraint is composed, control constraint set is composed of many controls, how to deal with that. And the other one is how to construct this function that represents the potential of the state that you're going to visit after applying this control, it's going to lead to. So those two challenges are common between stochastic problem and deterministic problem. However, what is new here is this stochastic quantity, WK, which lead the state after applying XK and UK, lead to a state to some next state, which is not fully certainly predicted, because in the deterministic system, at state XK, after applying UK, we know exactly where the next state is going to be. But now, because of the stochastic quantity, this next state becomes a stochastic quantity as well, right? As a result, the whole sum in the bracket is a stochastic quantity. We cannot minimize the stochastic quantity. Therefore, we need to compute its expectation. Next lecture, we're going to talk about something different, whereby this WK, instead of we compute its expectation with respect to a certain probability distribution, we're going to take a different view. The lecture after the next lecture, we're going to take a different view. But for stochastic problem, we assume this quantity, we have a probabilistic description of this quantity, and we want to minimize the expected value of this sum. And we will focus on the case where this function is the cost function of a base policy, pi, where pi, recall that given a finite horizon optimal control problem, pi is a sequence of functions that for each stage, at each stage, given a control, it prescribes a given a state, it prescribes a control that satisfies the control constraint set. So we focus on the case where this function is a cost function of a policy, which we call base policy. So jk plus 1 prime, comma pi means that the cost function of policy pi, starting from the state fx of xk, uk, and wk, starting at stage k plus 1, right? And unlike deterministic case, recall that in deterministic case for rollout, we use a function h, which represents the cost of heuristic. Here, we directly restrict it to the case that is a cost function of a policy we call base policy cost. So the policy pi used for rollout is called a base policy. And the policy, after this minimization, given the current state xk, we compute some control uk prime tilde, right? And this uk tilde defines a policy that at state xk, we apply this uk tilde, right? So this policy is denoted by pi tilde, and we call it rollout policy. And the notational convention is that typically we use tilde to represent rollout policy or approximation, a policy obtained while approximation in value space. Now here is the important fact, is that if we use as cost function approximation for J star, we use the base policy cost, then there is a cost improvement property. That is the cost function of the rollout policy obtained while this minimization at all state xk and all stage k, all of them are no more than the cost function of the base policy at the same stage and starting from the same state. And we're gonna go to the proof of this one shortly. And it holds. Remember, in the deterministic case, we have a similar result, but we impose some conditions like sequential improvement and sequential consistency. But here, I directly claim that the cost improvement property hold. And the reason is because we already restricted our attention to base policies. So it's not heuristic, it's not something more general, but rather is a policy. By policy, it means starting from the same state, you're gonna always give the same control. So it's consistent by its definition. And every mu 0, mu 1 is a function that maps x to a control that is feasible. Therefore, it already has a sequential consistency property. And so we don't need to impose any additional conditions. Now, because of the presence of this WK, things become more challenging. obviously. And the reason is that starting from the same xk, when we evaluate the potential of uk, and this quantity is the stochastic quantity, and wk can change, can take values from a set. And what makes it worse is that this term typically is not given as a closed form formula that you can just plug in and calculate, but instead it is approximated most of the time using a simulator, which means you need to run a lot of simulation using the base policy and average them over in order to calculate this value. And suppose that we have a finite horizon problem with number n, where n is a very large number, let's say 100. And in the initial stage, after when we explore some control u0, you need to evaluate the cost function of a base policy starting from some x1. So you run simulation and you want to evaluate this cost function exactly. Starting from x1, you have w1, and then x2, w2, and so on. As a result, for a single trajectory, it involves 99 random quantities. So when you calculate the cost function, the variance is going to be quite large. And how to deal with those is the subject of this lecture. So how do we try to approximate this function? One possibility is to use truncated rollout. Suppose that we have some sort of approximation of this cost, then instead of running all the way till the end, n, we may run 10 steps. And the benefit of that is that it only involves 10 random quantities rather than 99 random quantities. So it would be much easier to evaluate its value with smaller variance. Of course, it's not anymore a faithful sample of the cost function because it involves some terminal cost approximation. Other possibility is to use pruning and certainty equivalence. Pruning here means that we may prune some of the random quantities along the way, or prune some of the UK that we evaluate. And certainty equivalence is an important idea that we're gonna talk a little bit more later. Basically, it's instead of running random trajectories, instead we just fix the nominal values of WK plus 1. So starting from WK, we don't approximate WK, but use nominal values of starting from the next stage and so on. The other possibility is to use limited simulation. So instead of running this full blue, give enough same attention to all possible control, rather we use some heuristic or formula to give us guideline where to sample in the next sample and so on. And the prime example of those ideas are Monte Carlo Tree Search. We're going to talk about that briefly. Okay, before we go to the theory to prove this performance improvement, let's look at an interesting example, which is Backgammon. And this is, if not the first one, this is the first one that provide an in-depth, detailed analysis study of rollout methodology and investigated various remedy of simulation and so on, and demonstrated major success of rollout. So the Backgammon game. And let me remind you what this game is about. So for this game, it's a two-person game. And for convenience of this lecture, let's assume that we are playing this game against a fixed opponent. In 2 lectures, we're going to talk about the minimax problems and tell you how potentially how you can find this fixed opponent when you are competing with a strong opponent. But for the moment, for the purpose of this lecture, let's assume you are competing against a fixed opponent. So it's a one-person problem. And in this problem, the states involve two components. One is the board position, where all those both black represents one player and white represents another player. But also there is a stochastic component, which is a dice roll. So before you take action, you need to roll two dice, and which gonna tell you, given the dice roll, what are the possible move of pieces that is allowed, and according to the dice roll. So there is a stochastic quantity involved, and the stochastic disturbance is a dice roll. And at every state, which is the board position, and after the dice roll has been fixed, there are 20 to 40 different moves that can be made, which means there is a branching factor around 20 to 40. In addition to that, after you made the move, the opponent, even though it's a fixed opponent, it will roll the dice as well, which means the dice roll, there are 30 different situations. So 30 times 40, you have 1,200 branching factor, which is quite large, right? And as a result, this is a quite challenging problem. In the early 1990s, Tassaro, a researcher in IBM, developed a methodology whereby he used supervised learning to obtain a value network using our terminology today. And after obtaining that value network, he used one step or two steps look ahead to obtain a player. Now this player was very strong, defeated all the other computer programs at the time, Backgammon, and its performance is close to human champion, but cannot defeat human champion. So it's inferior to human champion. A few years later, that is 1996, he introduced a variant version of his preceding method, whereby essentially he introduced the truncated rollout form of the method. And in particular, he still rely on the value network, and he does not have a policy network, but instead he used one step look ahead with respect to that value network as base policy. So given that you obtain a value network, you run one step look ahead, and that defines a policy, right? And he used that as base policy. And he ran truncated rollout using that base policy. And after a few steps, that is supplemented by the value network he obtained. And he ran one step or two steps look ahead for this truncated rollout. As it turned out, after introducing this truncated rollout portion, the performance got a boost, and it can defeat human champion after introducing those rollout portion. Unfortunately, this rollout portion is just too slow because you need to run a lot of simulation, and each simulation, remember, the base policy is defined by using one step look ahead. So even run base policy, you need to run look ahead. So it's a excessive online Monte Carlo simulation. And bear in mind, this is mid of 1990s. So today's computer is not available yet. And at the time, for this program, he need to run months of simulation or training in order to get the value network. But still, it's extraordinary that he was able to put everything together and demonstrate clearly the rollout portion make a great difference, because the value network can give you some idea about the potential of different positions and so on, but rollout portion can basically provide better estimate about those positions. Okay, enough with the example. Let's go to the theory. We're going to prove that starting with the base policy, using one-step lookahead, we get a policy that is no worse than the base policy for all xk and k. And the following argument is highly parallel to the deterministic case. And similarly to the deterministic case, it only holds for untruncated version of rollout. Once you introduce terminal cost approximation, truncation, it does not hold anymore. Okay, and similarly, we prove by induction, starting with k equal to capital N, since both policy, the Jn is equal to the terminal stage cost G, so this inequality holds. And assuming it holds for k plus 1, the first formula is the dynamic programming equation for the rollout policy. So at the current stage, xk, we apply mu k tilde, and the cost of the rollout policy equal to the current stage cost plus the cost to go starting from the next stage. And the first inequality holds because the induction hypothesis, right? We have assumed this inequality holds for k plus 1. Therefore, by replacing this pi tilde with pi, and the taking expectation, recall that taking expectation means summing up terms with weights, which is given by the probability. So expectation preserve the inequality. So given that this value is smaller than this value for all x, k plus 1, so the inequality also holds. Now we go to the second equality. Recall that this mu k tilde is computed by running minimization, right? We try to find among all the feasible control, the one that attains the minimum, and assign that as the rollout policy control at state xk. Therefore, this term is equal to the minimum attained here. And since it's a minimum among all the UK, therefore it must be no more than the control of the base policy. Therefore, this inequality holds. And the last equality is the dynamic programming equation for the base policy, right? And therefore, the proof is concluded. And as you can see, the whole argument is pretty much the same as the deterministic case. And because we rely on this dynamic programming formula and so on, if we use truncated rollout, then the proof argument break down and does not apply. But in reality, typically, empirically, we see an improvement of rollout policy over base policy despite truncation. Okay, so as I alluded to earlier, there are a lot of challenges of the stochastic problem. The prime of them is how can we deal with the expectation calculation given that it is run by simulation. And we're going to consider one particular case where the control constraint set is finite. So there are finitely many UK, and for each UK, we compute its Q factor, which is this expression, essentially the right-hand side of the one-step look ahead, and we minimize over UK, and we want to find the UK that attains the minimum of among all the Q factor. Importantly, this is equivalent to compare Q factor differences. So if we manage to, instead of calculating those values, it's equivalent to simply compute the differences with different two Q factors and find the one that attains the minimum, right? So for each of this Q factor calculation requires, for each UK, we generate many sample disturbance trajectories, WK, K+1, till n-1, in order to estimate the Q factor by averaging over the samples we get. And in practice, the number of samples is finite. Therefore, the value we obtain is really a calculated estimate of the Q value, not its exact value, but calculated value is approximation of that value that involves stochastic variance. And this stochastic variance can damage our selection of control, because suppose for one control, it so happens in our samples, we have favorable W's, and in other control, we have a less favorable W's, and that can lead to incorrect selection of the control. As a result, we should aim to reduce the variance of calculated Q factor differences for control pairs. So given any control pair UK and UK prime, we would like to reduce the variance of this estimated value or estimated Q factor differences. For variance reduction purpose, it is often best to use the same sample disturbance trajectories for all UK. Now here, we need to make some implicit assumption. That is, all the random disturbance trajectories can be generated under different control. For example, because if we're going to evaluate different Q factors, we're going to, here UK and UK prime is not the same, which means XK+1 and here, generated after applying UK, may be different from the XK+1 prime generated after applying UK prime, right? So what we need is all those random disturbances can be generated regardless of the state that we land on, and they should share the same distribution. So essentially, the same random variable, the same random disturbance should have the same distribution independent of the state or independent of control. And more details you can see in the textbook. But under this assumption, then it's better to use the same sample disturbance trajectories when evaluating different UKs. Intuitively, this means if the sample trajectories are favorable case, then this favorable case is considered for all UK and UK prime, right? Not for a particular control. Let's consider a simple example. We want to calculate and compare Q1 and Q2, okay? And we don't have exact values of Q1 and Q2, but rather we can estimate or we can measure Q1 and Q2 with some random noise. So we can measure Q1 through this formula, Q1 plus W1. So the measurement of Q1 involve a random quantity. And the measurement of Q2 also involve a random quantity. And suppose W1 and W2, both of them share the same probability distribution, then if we sample independently W1 and W2, and if W1 is the sample of W1 is a favorable case and W2 is unfavorable case, then this gonna create an error when we estimate Q1 minus Q2. Suppose instead we sample according to the distribution W and use the same W value for both W1 and W2 to calculate the measurement of Q1 and Q2, then the difference of S1 minus S2 would be equal to the Q1 minus Q2. So how this can be applied to estimating the Q factors? Suppose that we have two control, UK and UK prime, we would like to evaluate their Q factors. We sample a lot of disturbance trajectories. Let's say we sample 50 of them. And we use the same random trajectory to calculate the estimate of Q for both UK and UK prime. And by doing that, we can reduce the variance of the difference of them. So this is the simple idea of this method. Yes, please. Okay, let's say Q1 is in fact the smaller value we want to compute, right? And Q2 is the larger value. And suppose that we have the W1 selected when we measure Q1. The W1 we use is unfavorable case, which is the large value, whereas W2 is a favorable case, let's say it's 0, then it may be that S1, because of the arrow here, it turned out to be larger than S2. So this is how this example illustrates. And in terms of mathematical argument, there is a proof to show that by using the common random variable, the variance can be reduced. Or essentially, you can think it as you use a common random quantity to evaluate two different situations, whereas in the naive implementation, you use one random quantity to evaluate one situation and another random quantity to evaluate another situation, even though they are sampled from the same distribution, but each one of them carries some variance of its own. So that can cause a problem. Any other questions? Yes.
So W1 and W2 are random variables.
Yes.
And
so we are assuming that they share the same probability distribution.
one different.
I mean, if they use different distribution, then this whole idea does not apply, right? And that's why I'm saying that in order to use the same sample distribution disturbance trajectories, we need to make sure the distribution of WK plus 1 does not depend on XK plus 1. Because given the current state XK, we apply UK, we have a state XK plus 1, right? And given the state XK and UK prime, we have a different state XK plus 1 prime. And if WK plus 1 depends on the state, then we cannot use the same sample disturbance trajectory for different situation, right? In the extreme case, this WK plus 1 may be possible to generate in 1xk plus 1, but totally impossible to be generated in the other case. So you cannot use the same sample trajectory, sample disturbance trajectory for two different cases. And that's why we need to make the assumption the disturbance distribution does not depend on xk and uk in order to use the common disturbance trajectories. And similarly here, if W1 and W2 do not share the probability distribution, then we cannot use the same for both, right?
If they have the same expectation.
You still cannot. You still cannot. I mean, okay, having the same distribution does not even mean they share the same value, right? You can have distribution both, the expectation both equal to 0, but one take the value minus 0.5 and 0.5, and the other take the value minus 1 and 1. So how can you use the common value, common disturbance trajectory, right? You cannot. Okay.
You are saying the stochasticity doesn't depend on the state or action.
Yes.
But like, but most of the situation, like the randomness is kind of depends on like which state you are or like what kind of action you take.
Yeah, in which case you cannot use it. But there are still a lot of cases where the random quantity is kind of, independent, standalone, and then you can use the common random quantity. Okay. Okay. So let's go to multi-step lookahead. Stochastic rollout with multi-step lookahead. And similar as the deterministic case, we have, we would like to, given the current state xk, we want to run a minimization over L steps with the future captured by some cost function approximation. And in the context of rollout, this is the base policy cost. However, here is a major difference compared with one-step lookahead. So in one-step lookahead, we minimize over UK, right? Given that the problem is stochastic, which means after applying xk and uk, there are some stochastic quantity generated, which gonna lead to a state we do not know beforehand. Therefore, for all the subsequent states, we need to compute its policy rather than, instead of computing minimizing over a control sequence, as you will see in the deterministic case, here, given the current state for the current control, UK, it's still a control, but all the subsequent stages, they are policies. We minimize over policies, and that's more challenging than the deterministic case. So essentially, this minimization problem is a dynamic programming problem itself. And if we are dealing with finite horizon problem, then typically this L is much smaller than the real horizon of the problem, this capital N, right? But still, this can be a challenging problem. And we take for granted that additional cost improvement is obtained with longer lookahead. So with longer lookahead, the less we rely on the terminal cost approximation, the better our rollout policy is in terms of its cost. But as we have seen in our preceding lectures, there can be exceptions. Some are artificially created academic example, but in this most likely sequence situation, we do see with multi-step lookahead, we get worse performance. And apart from this minimization over functions, another big issue is that the necessary simulation increase rapidly with the length of lookahead. Because note that given the current state, xk, applying UK for each UK, there is a WK and all the subsequent state are not deterministic, but rather stochastic. It can, there is a lot, even if there is a small branching factor with not too large L, the number that we need to explore or compute starting from xk plus L can be gigantic. So it grows exponentially. And this is a big issue. And for each one of them, if we want run simulation, there are going to be a lot of simulation. So how to deal with this? One possibility is truncated rollout. As I mentioned earlier, instead of running base policy all the way till the end, we may run a few steps, and after which we plug in some cost function approximation, just like Thesaurus TD Gammon. And the other possibility is to use certainty equivalence approximation, whereby for WK, we still consider its various values and try to compute the expectation. But for all the subsequent stages, we use some nominal values of WK plus 1 until WM minus 1. As a result, very importantly, this part become minimizing over control again. It's not minimizing over policies, and that's much easier. And the other possibility is Monte Carlo Tree Search, we will go to shortly. There are not much we can say about truncation. As I mentioned, since our proof rely on Bellman's equation and so on, so after you applying truncation, then the performance guarantee lost. However, it is still maintains the Newton's method character of approximation in value space and tend to improve the performance and stability of the rollout policy relative to approximation in value space without rollout. So including rollout portion typically helps. Yes?
When you fix WK plus 1 to WN minus 1, then essentially you are removing the stochasticity of the K plus 1 step, right?
Yes, but, okay, that's a good question. The important thing here is we still keep WK, which means the immediate stochasticity or different situations caused by the stochastic nature of WK is still considered. It's just beyond that into the future, we don't consider it. And since we still consider WK, which means this Newton step interpretation, you minimize over certain function and you get this tangent line in the linear quadratic case still remain to be true. And that's why typically you can still expect a good performance. It's just that all the subsequent terms, instead of calculating it exactly by considering various values of K plus 1 until Wn, that we don't consider. So in a way, it's this term, we have a rough approximation, but we still need to take expectation because WK is still present and this Newton method interpretation still remain valid.
It would be close to a single step minimization, like one step to go ahead.
Well, not exactly, because basically you still consider minimizing over L minus 1 stage policy controls, right? You still consider all the subsequent stage stuff. And it's just that the situation you consider has limited to one particular case, not a lot of them. We're going to go into a little bit more detail of this. Okay, well, next to discuss certainty equivalence and Monte Carlo tree search. And as I mentioned, certainty equivalence maintains the Newton step character, whereas Monte Carlo tree search does not. Okay, now here, hopefully this picture is going to give you a more clear idea of what is going on for certainty equivalence. Suppose that we just run the multi-step lookahead without certainty equivalence. At current state, okay, we change the subscript to 0. Suppose that we are at initial stage. At x0, suppose we have two different controls to consider. And for different control, suppose that we also have two different W0 values that we need to consider. So basically, compared with deterministic case, from every state X, we have one branching. Now, because of the stochastic nature of the problem, we have two layers of branching, right? One branching corresponds to the control, and one branching corresponds to the stochastic quantity. So starting from x0, after two layers of branching, we get to x1, and we repeat this procedure, we get to x2, and so on. And not only that, after this layers of branching, we get to XL, all possible XL. And from there, we run base policy, which means from every XL, we need to run stochastic simulation. So not one trajectory, but multiple trajectory and average them over. Now compare with this, if we fix the stochastic quantities at nominal values, starting from xk, wk plus 1, and Monte Carlo average many trajectories of the form, then we look at the same figure. From the current stage, we have two branching, U and W. After that, the lookahead tree looks nearly identical or exactly identical to the deterministic case because the random quantity here, the branching has been reduced to one pass, so there's no branch anymore. And as a result, here in this case, it's 2L layers of lookahead tree. Whereas in this one, if we fix the same L, it's L plus 1 layers. And if we have, our restriction is on the computation time, and to get to the same level of breadth, we can go as far as 2L step lookahead rather than L step lookahead. So after 2L minus 1 step lookahead, we'll get to the same numbers of the leaves here compared with this one. And another saving benefit is that starting from here, instead of running stochastic simulation, where the value of them are averaged over multiple trajectories. So starting from here, let's say from this XL, we run base policy, multiple samples all the way till the end of N, and we average them over in order to calculate the value J K plus L plus or JL pi value. Here, we run one trajectory because we fix the value of a random quantity to its nominal value. So it's deterministic simulation rather than stochastic simulation. So there are two big savings in the stochastic certainty equivalence method. Therefore, it requires much less simulation. Any questions here? Okay. Let's go to Monte Carlo Tree Search. Monte Carlo Tree Search is a very popular method for saving simulation, or given the fixed amount of simulation budget, you want to find a way to decide where you're gonna allocate next sample. And it's an approximation of lookahead minimization, and the motivation is to save simulation effort. We assumed equal effort up until this point. We assumed equal effort for evaluating Q factors of all controls at state xk. As mentioned earlier, all those Q factors cannot be calculated exactly in most cases, so you need to be evaluated empirically by running samples and average them over, right? And there are drawbacks. Some controls may be clearly inferior to others and may not be worth as much sampling effort. And suppose after one or two sample, it's so obvious that this is just a bad choice, and you should not do that. And let's give an example. Suppose you plan to travel to the other side of the country, and it's obviously walking is not a good idea. I mean, things like this, it's quite obvious after you give a sample or give a little bit thought, you realize, okay, even though this one is feasible, it's just not a good idea to try. The other case is some controls that appear to be promising may be worth exploring better through more sampling and also even multi-step lookahead. Suppose that we want to choose a control UK, and clearly there are a few inferior ones, and there are two that are most promising. And by calculating minimization, essentially we want to find the best among those two, right? So we need to steer all our sampling effort to those two controls in order to give accurate evaluation of those two and to make our decision in the end. So that's the case here. And Monte Carlo Tree Search is a form of approximate lookahead minimization that try to economize in simulation time. It involves adaptive simulation, where the simulation effort adapted to the perceived quality of different controls. And it aims to balance exploitation, which is extra simulation effort on controls that looks promising, and exploration, which is adequate exploration of the potential of all controls. And those two words appear in both offline training process and online play process, and their role are slightly different. In the offline training process, when you collect the sample, you want to have adequate exploration in order to collect enough sample to get a good training process to either be it a policy or cost function approximation. Whereas in the context of Monte Carlo Tree Search, which is the online play algorithm, suppose typically there is a limited budget of sampling that you can do, and you want to steer the sample towards and you want to make sure that the limited amount of simulation covers the potential of all controls. For example, several of you have proposed mini research topic of using LLM-related applications, where LLM can play the role of either cost function approximation or base policy, right? And suppose that, or even you have offline some LLM on your computer or the server, then every time you query the model, is not free of charge, right? You still involve a lot of calculation, computation, and in the other situation, you may not even have that model locally installed in your computer, so you need to query some online service which costs money. And therefore, you want to, given the limited budget of how many times you can query the language model, or how many times you can run the base policy and so on. You want to make sure that the effort of sampling is divided such that adequate attention is given to all the controls, and at the same time try to give a fair evaluation of the promising controls. And Monte Carlo Tree Search, just like simplified rollout and pruning, does not directly improve performance. Here are some misconceptions in literature. Sometimes people claim that Monte Carlo Tree Search directly improve performance, which is not right, because you can imagine that instead of running Monte Carlo Tree Search to allocate effort of sampling cleverly, heuristically to various controls. By contrast, suppose that there's no limitation on sampling. You just throw a lot of sample, use a lot of sample for every single control, then you will get a better estimate of the Q factors, and obviously you will get a better performance. What does it mean here? Improve performance, it means that if you have a limit of sampling budget, and if you manage to allocate all those sampling cleverly, or even allow you to do multi-step look ahead, it can provide better performance. So it does not provide performance improvement directly, but rather indirectly if you run cleverly with Monte Carlo Tree Search and do multi-step look ahead. Okay, but let's use one-step look ahead as an example. And suppose that given the current state xk, we have 3 different controls, and start from applying different controls, we run simulations and so on. So Monte Carlo Tree Search provides an economical sampling policy to estimate those Q factors, where each Q factor is this expected value, right? And the simulation scheme is to pick a control U in some way and generate a single sample of its Q factor. So instead of allocate equally sampling effort to every control, for the Q factor of every control, we sequentially decide which control we select to generate the next sampling trajectory to improve the estimate of that Q factor. So suppose that we already have n samples, and for each U, we denote QUN, its empirical mean, the empirical mean of its Q factor of the control U. So the total sample value divided by total number of samples corresponding to U. Essentially, for one sample, we get a sample of, for one trajectory. After one trajectory, we get one sample of the Q factor, and after n sample, we just average them over, right? It's the empirical mean. And this provides an indicator of how promising the control is, because this is empirical mean of the Q factor we are computing. So we use it as exploitation index, a measure of quality of U. We could use the estimate to select control to sample next, but the question is, in the previous sampling procedure, we may overlook some control, which in fact is better than the ones we have evaluated now. So we want to make sure that we do not overlook some less explored controls. How can we do that? Well, in addition to the exploitation index, which is the empirical mean of the Q factor we want to compute, we introduce an exploration index. And a popular, which is some sort of semi-heuristic strategy, is to sample the next control U that minimize the sum of those two indices, where RUN is exploration index. RUN is based on a confidence interval formula that is developed within the context of multi-armed bandit. Depends on sample count SU of control U. So for example, after in total sampled N Q factors, for the control U, the number is SU, then the smaller the number this SU is, the less this control U is explored, right? So this number should be larger in order to be in favor of exploring this control U more. And one of the formula, which is called upper confidence bound, set this value to be a scalar, minus scalar of this expression, where C is a positive constant, typically selected empirically. And in literature, C equal to square root of 2 has been suggested, assuming the values of Q are normalized to take the value within the interval, within a range from -1 to 0. Monte Carlo Tree Search with UCB rule has been extended somewhat heuristically to multi-step lookahead, and in some important application context has been useful. And one example is AlphaZero, but in fact, in AlphaZero, it used a different formula, which again, based on a heuristic argument. Note that during this process, suppose that we have in total 100 sample budget. During this process, we minimize among those two quantities and to find what is the next control to select to evaluate, right? After we used up all the sampling budget, where N equal to the number of sampling budget, then at that point, we select our control based on our sampling efforts, right? And at that point, we don't minimize over the sums of exploration indices, but rather we minimize over the Qs only, because all those Qs would be the empirical estimate of the Q factors that we minimize. Okay, any questions here? All right, let's get a break, and we will get back in 15 minutes to talk about adaptive control and its application to Wordle. All right, let's get started with second half of the lecture. Now we're going to focus on a different type of problem, which is adaptive control problem, where we formulated it as a POMDP problem. And then we're going to introduce rollout methodology to address this type of problem. And after that, we're going to demonstrate how this problem can be, how this method can be applied to solve a type of puzzles called Wordle that we have touched upon earlier. Okay. So in this problem, we have a deterministic system, xk plus 1 equal to fk of xk, theta, and uk. The theta is an unknown parameter taken from a set, theta 1 into theta m, finitely many. And we know this set. We just do not know which parameter theta is in effect right now. And we want to figure it out. And we view theta as part of the augmented state, xk and theta, that is partially observed. So we know xk, but we do not know theta. And theta is a fixed value, it's a fixed number. So it's selected from the set. This set we know, we just do not know what the number of theta is. And to address this problem, a POMDP formulation goes as follows. Given all the information we collected until k stage, which is x0, x1 until xk, as well as the control u0, u1 until uk minus 1, that is the information vector, we estimate online what is the probability of the actual theta equal to theta I. And this is the belief state. So given the system state xk and parameters theta, the state xk we can observe, and based on the xk, we use a belief estimator. We're going to go into details of this a bit later. And we have a belief of the probability of theta equal to any one of them. And based on this belief and the xk we can estimate, or we can observe, we define a controller that is a function of xk and bk in order to obtain a control and apply it to the system. This is a finite horizon optimal control problem. As a result, the exact dynamic programming algorithm in principle can be applied, whereby we use as state the information vector ik, and at the given information state ik, we minimize over the control uk, where the right-hand side of Bellman's equation looks like this. It's a sum of the Q factors of this form, whereby the weight of the sum is the belief of the true theta equal to theta I, and you plug in that theta I as the stage cost as well as the optimal cost of future state. And this is the information vector at k plus 1 stage, right? It's the current information vector plus the next state that can be observed, as well as the control you apply. And they are averaged over all parameter value theta I, weighted by the current belief values. So the probability of theta equal to theta I given the current information. And despite being quite similar to what we have seen before, this problem can be even more challenging. And one of the primary reasons is the information vector is expanding. So given the current state, starting with x0, the information state at k equal to 1 become x0, u0, x1. And then the next state, you're going to append also x1 and x1 and u1 and so on. So it increases. And the size of state space can be gigantic. Not to mention, it's not easy to calculate the belief vector. So typically, we need to resort to approximation in value space and to solve the problem, approximate approaches to solve the problem. And for approximation in value space, instead of using the optimal cost of the problem with the state being the information vector, we use approximations j tilde I. This means we take for granted that the value, parameter value theta is equal to theta I. And as a result, the state become xk plus 1 rather than the information vector. And we minimize over UK to obtain the one-step lookahead policy. There are multiple choices of this J tilde I. And one possibility is that it's a cost function of the optimal policy corresponding to theta I. So suppose we know the value of theta equal to theta I, and we solve this fully observable problem because now we know the value of theta and it become a deterministic problem. We can solve it exactly, suppose. Then we can get this J tilde I, and we need to solve m different of m such problems to obtain the J tilde I, and we use that in place of J star. So this is one example. The second example is that it's a cost of a non-policy, again, assuming theta equal to theta I. So for different theta I, we may use a different policy defined, but it is possible to use a common policy regardless of the value of theta, and we will see that later. But in any case, this is a rollout. Let's see how rollout can be applied for adaptive control with this POMDP formulation. Given the current state, xk, which we can observe, suppose that there are two different control options for us to select, UK and UK prime, right? Suppose further that there are two different parameters that we are not sure which one it is. So for UK, we assume theta is equal to theta 1 and run the base policy pi 1 applied to theta 1 to the case where theta equal to theta 1, and we get a trajectory, get a sample of Q. And similarly, for theta equal to theta 2, we apply the base policy that tailored for theta 2 and run a trajectory. And let's assume this one have 70% of chance of being the theta, and this one have 30% of chance of being the true theta, given our current belief. Then we just sum over the empirical values of those two trajectories, the sampled values of those two trajectories, weighted by the belief numbers 0.7 and 0.3, right? And we get the average Q factor of UK in this form, where each QK is a trajectory assuming theta equal to theta I, and it's a immediate stage cost of the stage plus all the future cost of starting from the next state using the base policy that is tailored for theta equal to theta 1. And after enumerating all the situations, all the thetas, we average them over using the weight that is our current belief that theta equal to theta I. Note that this is just the basic form. Okay, after averaging, find the average Q factors, QK hat, our control, UK tilde, is selected by minimizing among the estimated Q factors, average Q factors. And this is the standard form of rollout. And obviously we have introduced a lot of variants of rollout, including simplified rollout by considering a subset rather than the full set of the control, as well as rollout involving multiple policies and so on. So all of them applies here as well. All right. So with that, let's go to the example Wordle, and I'm going to demonstrate how this approach can be applied to solve the puzzle. How many of you have played with this game? Okay, a lot of them, most of them. but I will just briefly go through it. And every day there is a mystery word selected from a mystery list composed of 2,315 words. And each one of them consists of 5 letters. The list of this mystery of this 3,000 words, 2,000 words are known to the public. And in our discussion, we assume, and it's widely believed as well, the mystery word is generated randomly according to a uniform distribution over the mystery list. As a player, our goal is to guess the mystery word in 6 attempts. Each guessed attempt consists of a word from the non-guessed list of 12,000 words with other potential constraints, and I will come to this shortly. Once you give a guess word as input, there are feedback provided by the program. And it's gonna highlight some of the letters in your guess letter. If a letter highlighted in yellow, that means the same letter is present in the mystery word at a different location. If it's highlighted in green, well, then congratulations, you get the same letter that is present in the mystery word at the same location. So in this case, the mystery word is present, the letter I is present in the mystery word, but at the different location. So the other 4 locations. And in this case, E and R are present in the mystery word and at the same locations. And if you get something like all of them are gray, then that means you get nothing. And our goal is to minimize the expected number of guesses to solve the puzzle. And we want to take as little guesses as possible to find out what is a mystery word. There are 2 modes of the program. One is the easy mode and one is the hard mode. In the easy mode, essentially after each guess, you can select freely this 12,000 words as another guess, as a guess word for your next attempt. On the other hand, in the hard mode, all the revealed hints must be used in subsequent guesses, which means in this case, after you give the guess and the feedback tells you that E is present in the mystery word at the end of the word, then the next guess cannot be freely selected from this 12,000 word, but rather you have to select the words or guess the word with E in the end of the of your guess. So it's the options that you can select are greatly restricted. You may wonder why this 12,000 words, you use the guess list of 12,000 words rather than this 2,300 words, right? One possibility is that you may select some word that give you, even though it's not in the mystery list, but it give you more information about what could be the letter, what could be the mystery word. And using the words in the mystery list may not provide as much information as some of those in the guest list. Okay, I hope it's clear to all of you at this stage. Now, given this practical problem, and we want to address it mathematically, then we need to formulate it as a mathematical problem, and we will formulate it as a POMDP problem. And to do that, let's see. We discussed earlier this POMDP formulation involving xk and theta and uk, right? So what is the theta? It's quite obvious. It's a mystery word that we want to guess. It's an unknown and fixed parameter. As for xk, there are a lot of options you can choose. You can even choose it as an image of the feedback. But of course, that's not the most convenient way to do. The one we select as the state is the list of possible mystery words, given the guesses so far and given the hints provided by the program so far. Why? Because given all the hints, which letters are present in the mystery words, which one are not, and where are those letters, and so on. All of them, all of those information helps us to narrow down what is the potential mystery word. And it will be a list that is a subset of the initial mystery list, right? So using as state, the possible mystery words is sufficient. And as in the previous case, we treat theta as part of the augmented states that's partially observable. We have xk that's observable, and theta is the one we want to choose. And the control uk selected is the selected guess word we're gonna use as input to the program. And the control constraint applies only in the hard mode. As I mentioned, in the case of easy mode, you can select among those 12,000 guess word, so there's no control constraint present. Whereas in the hard mode, there are restrictions on which one you can choose as your control. Given all those information, the system equation, which given a current xk and suppose a value of mystery word theta equal to theta I, and given the next guess, the next state, which is the new list of mystery word, can be defined accordingly. And the stage cost is simply 1 at each stage and 0 after you find out what is the guessed word. Or in other words, the state xk narrowed down to a set that composed of only the mystery word. And in that case, you already find out what is a mystery word, and the cost is 0 afterwards. And since it's 6 guesses, k equal from 0 to 5. And we can have the belief space representation. Since we have supposed or assumed that the mystery word is generated randomly from the mystery list according to a uniform distribution, an important fact is that throughout this process, the belief maintains a uniform distribution. The theta maintains a uniform distribution over the set of feasible mystery words. So it's always a uniform distribution. Initially, this distribution is 1 over 2,300 for each of those words. After, let's say you choose a control, or choose this word, suppose that the feasible words has narrowed down to 500, then the probability of each one of them being the true mystery word is 1 over 500. So it's always uniform distribution. It can be solved by dynamic programming, but it's a daunting computational task. And according to a study, it requires days of parallel computation where the code was written in C++ and running nonstop for several days to solve this problem and get the optimal. And this is only 6 words, 5-letter words. And you can imagine if it's 6-letter words or if the distribution is more complicated, how long time you're going to use to solve it. Okay, now let's see how we can address this problem using the rollout algorithm we introduced a moment ago. we will rely on a noun-based policy. And the noun-based policy studied in the paper referred to in the textbook involves 3 different base policies. One is maximum information gain, and based on some information theoretic argument, and most rapid decrease, which is rely on trying to minimize the number of mystery word contained in the list, and the other one is the greatest expected probability. All you need to remember is there are some base policies, and you can get the software. So given the current list, as input, those base policies can give you the guess of what would be the guess word it suggests, and also give you the preference of other words over other words, given some indices about which one is most probable and or favorable according to this heuristic, and which one is the second favorable, and so on and so forth. And this method select the most favorable words according to certain criteria. So given the current state, which is the current list of all the feasible words, for every guess that is allowed, in the case of easy mode, it will be 12,000. And in the case of hard mode, it will be the number that contained in the XK. And for every one of them, you evaluate, suppose that theta equal to the first theta 1 and equal to the second theta 2. Essentially, the branching here, again, is the number that contained in the XK. So all possible mystery words. And suppose the mystery words is theta 1, you run the base policy and see how many steps it requires for this particular base policy to solve the problem, or even not solve the problem, and run all the way till n guesses, 6 guesses in the end. So you do the same thing for the second possible mystery word. Suppose the mystery word equal to the theta 2. For each of the feasible guess, you run the given base policy starting from the next state, and to get a sample trajectory of this Q factor. So again, the branching factor here is equal to the number contained in the current list. And as I mentioned earlier, throughout this calculation, the belief state, the theta distribution over the feasible mystery word remains a uniform distribution. So for every theta, its probability is 1 over the number contained in the feasible list. For every one of them, you assume theta equal to theta 1, theta equal to theta 2, and so on. You run the base policy and see how many guesses you need to get the right word, or even exhaust the 6 guesses. And that gives a Q trajectory, and you average them over using this weighted formula, essentially sum them up and divide it by the number in XK. And then you select UK tilde by minimizing those averaged Q factors. Here we use this important fact that belief remains uniform distribution. Therefore, we can just add up all those Q numbers and divide by the number contained in XK. In more challenging situations, suppose the distribution is not uniform, then this thing need to be estimated using some other formulas. But in either case, calculating this estimated average Q factor can be done quite conveniently compared with the DP calculation, of course. But here, the branching factor here can be way too large. So suppose either in the easy mode or in the challenging mode, the initial feasible numbers are 12,000, right? And for 12,000 of them, each one you simulate all the possible mystery word, which is 2,300. So in total, the number of simulation you need to run is 12,000 times 2,300, which is too many. Therefore, it's reasonable to consider simplifying rollout. Instead of considering all the feasible control, but rather you consider only the subset of feasible controls suggested by the same base policy. As I mentioned, given the current list, the base policy gonna rank the feasible controls according to certain criteria and choose the best one, right? So instead of considering all the control, we may select the top 5 controls suggested by the base policy and construct this UK hat and minimize among those controls rather than all of them. And I claim by doing so, I still have the cost improvement property maintained compared with examining all the control. Can someone explain why still maintain cost improvement property? Yes? Okay. You're thinking.
Base policy already bans.
Sorry?
The base policy already bans.
Yeah, exactly. That's the whole point. So the base policy is already contained in this set because how the base policy select the control is that you rank the preference, give preferences according to some criteria, and you choose the one that it has the highest ranking. So given that we choose the top 5, and the number 1 is already given by the base policy, therefore the base policy case is already considered. And if you go back to the proof of performance improvement, you can see that replacing UK of XK by UK hat of XK does not break down the argument. Okay. So how does it perform? We tested 3 base policies, as mentioned earlier, and we also compared it against the optimal policy, optimal score. And here we use the solid line as base policy result and the dashed line as of the same color coding as the corresponding rollout policy. And as you can see, there are 1, 2, 3, 4, 5, 6 different cases. Why 6? Because we did not plot the cost of the heuristic GEP. And the reason is because it's too large. It's a bad base policy. However, the important thing here is even with this bad base policy, you can see its corresponding rollout performance given the different opening words are still quite comparable to other much better base policy. So we get to the conclusion that rollout is insensitive to the base policy. And the other thing obviously is all the cost obtained by base policy is very close to optimal, starting with different opening words. But of course, the opening words is the first control U0, right? So you compare with the U0 equal to the optimal, you see our score obtained by rollout, the best one of them is 3.52, which is very close, 0.5% of the, if I'm not wrong, of the optimal. So it's very close. And the computation time is 1 to 3 seconds. It's not much. And can achieve this good performance and insensitive to the base policy. Intuitively, you can have some idea of why it's insensitive to the base policy from the exercise you have done with a linear quadratic problem, because you can imagine the Bellman curve of this problem is fairly flat once you go to the right side of Bellman's equation, right? So even the base policy you choose is far from optimal. Since the Bellman curve is quite flat, you do one step look ahead, you have this very flat curve going forward and give you the solution which is very close to optimal. And the other significant thing is its performance is not impacted by the drastic reduction of feasible gas to consider. As I mentioned, the number of control contained in the control set can be as large as 12,000. And we only consider in this computational study, we only consider five of them. So it's a gigantic reduction. Yet the performance is quite comparable. And in the paper, there are more details of this, and I won't talk further. And as I mentioned earlier, without the uniform initial belief distribution assumption and some small variation of the problem structure, the exact solution would be impossible. It would be too difficult to solve. And 2 days, the challenge, computational demand increase exponentially in dynamic programming and optimal control applications. So with slight twist of the problem, either the scale of the distribution, scale of the state space become larger, or the belief, initial belief become more difficult to calculate, it would not be possible to solve exactly. Whereas the rollout can solve near optimally the puzzle and its variance online much faster. I want to mention, okay, I talk a lot about this program, but this is not my work. It's actually some of the former students of this course several years ago, and they are PhD student sitting in 5th floor. And this is a product of their term paper. So after they have done a great job to implement and test out, it ended up as a publication together with the professor. So if this is the ideal scenario you should strive for, but at the same time, important thing is you apply the principled approach introduced in the course, and also what you have studied in literature, and try to address the problem mathematically and systematically. Okay, so as it turned out, the best opening word is salad, which I look it up. It's a helmet. That's the answer. All right. About the next lecture, we're going to talk about aggregation with representative state for both MDP and POMDP. And we talk about aggregation, this covered the aggregation topic many years ago, 2022. And we have been thinking how to apply this method to a reasonably challenging problem. And thanks to our guest lecturer, which going to deliver the lecture next week, King, sitting behind. And he managed to pull it off and apply it to a very challenging problem that involved POMDP and gigantic state and control space and observation space. And he's gonna also cover general aggregation and feature-based aggregation, whereby you introduce some sort of feature to group together the states in order to obtain a smaller scale problem. And he's gonna apply it to cybersecurity and other problems. So to help yourself prepared, you can read sections 3.6 of the course book. And you can also watch the lecture 12, 2022 version of the course. Okay, thank you for your time.